Hi everybody and welcome to a new exciting video in the Deep Learning for Audio with Python series. This time we're going to talk about computation in neural networks. I'm going to introduce you the Multilayer Perceptron, which is a simple neural network, and we're going to see how it works and the math behind it. So to get started, let's take a look at an old friend, the artificial neuron. So if you remember, we saw that an artificial neuron is a computational unit that's able to process some information and do some transformation on it. Well, the question is, so if the artificial neuron is a computational unit, why do we need a neural network? Isn't an artificial neuron good enough by itself? Well, it turns out that if you want to work on quite complex problems, you want to scale up to networks of neurons or neural networks, because a single neuron is really good if you are dealing with linear problems. But if you're dealing with more complex problems like real world problems or where there's a lot of like non-linearity in it, well, a single neuron it's not going to cut it. You're going to need a network of neurons which work together. And so artificial neural networks can reproduce highly nonlinear functions and can help us solve highly nonlinear problems. Cool. So let's take a look at the fundamental components of an artificial neural network. So we have obviously the neurons, and we've seen the math of a single neuron. And then these neurons are organized together into layers. And we have different types of layers. So we have the input layer, which is the layer where we provide information signal into the network first. Then we have a bunch of hidden layers, and so these hidden layers are layers of neurons organized and which are hidden because they are just like at the center within like the topology of the neural network. And then we have an output layer, which is the layer that we use to get information out of the network. And this one, which we like, this network that we have here also has a lot of weighted connections, and the weighted connections are these links here that we have among all of these neurons. And in this case we have a fully connected network because each neuron is connected to all other neurons in subsequent layers, as you can see it. For example, like this neuron here is connected to this neuron here, to this neuron here, and to this neuron down here. So this is a fully connected neural network. And then another component that we saw already when we talked about artificial neurons are the activation functions. And these functions are fundamental to process the incoming information that gets into the neurons. So a specific type of neural network, which is like very, very common, and it was like one of the first neural networks that was somehow engineered back in the day. It's called the multi-layer perceptron. Here the topology of the network is quite simple because you have a bunch of layers, and so you have an input layer, you can have one or multiple hidden layers, and then you have an output layer. And the idea basically is that the information travels from left to right, and this is a type of feed forward network because the information, as I said, gets in to the input layer and then travels all the way back to the output layer. So let's take a look at the computation in multi-layer perceptron. So as we said, information gets in through the input layer, gets fed into the network, then it travels all the way through the hidden layers. Here we have only one. If we have multiple, then it travels through all of the different hidden layers one by one, and then it gets out through the output layer. So we have this left to right information processing. Right. So in the multilayer perception, like the fundamental aspects of computation are the weights, the net inputs, which are like the sum of the weighted inputs, as we saw in the video about the artificial neurons. And then we have the activations, which are those functions which transform the incoming information and produce an output that the neurons provide to the next layer. So let's see them in context. So here we have our nice multilayer perception neural network, and here, as you can see, we have this uppercase W1 and uppercase W2. These are the weights. In the case of W1, we have, these are like the weights for all the connections between the inputs, so x1 and x2, and the hidden layer, so the s1, s2, and s3 neurons. And as you can see here, we can indicate these connections, these weights, using lowercase w11, lowercase w12, and so on and so forth. But how do we conveniently represent all of this information, all of these weights? Well, we can use our old friends, the matrices. So W1 can be written in this case as a 2x3 matrix. So we have 2 rows and 3 columns here. And W11 represents the connection, the weight of the connection between the input x1 and the first neuron in the hidden layer, so S1. Then we have W12, and that is the connection between X1 and S2. W13, it's the connection between X1 and S3. And as you can see here, we can look at these matrices. And if we consider only the rows, we're basically looking at all of the connections of one neuron from the initial layer into the second layer. Then if we look down here, we'll see that on the second row, we have all the connections of X2 with S1, S2, and S3. But now, if we look at this matrix column-wise, we can see that W11 and W21 are the incoming connections of S1 with regard to X1 and X2 to basically all of the incoming inputs. Good. So as you see here, for the first time, matrices are very important for describing how neural networks work, because it's a very convenient way of packaging up a lot of information about weights and a bunch of like other parameters as well. Cool. So we said weights are like the first very important element of a neural network, and specifically in this case of a multi-layer perceptron. Then we also have the net inputs. Now, we saw the net inputs in the case of a single artificial neuron. So what happens, the question is, what happens with a layer of neurons? Then in order to get all the net inputs, we want to multiply, in the case of H2, which is the net input for the second layer, for the hidden layer here, we need to do a matrix multiplication between the input vector and the weight one matrix. And this is like the we can rewrite this equation here like this. And so we have a row vector x1, x2, which is like these two guys here. So it's basically the input vector. And here we have our nice weight matrix. Now, if we perform the matrix multiplication there, we get a row vector, a three-dimensional row vector, where the first element here, x1 w1 plus x2 w21, is the net input h1. So it's basically the net input for the first neuron, s1. And then we have the second element here, so x1 w12 plus x2 w22. It corresponds to H2, which is the net input for S2, and same thing for H3 here. That's given by this nice like formula down here. Now, if you don't know how to perform matrix multiplications, don't worry, just go back to the previous video because I went into some details into vector and matrix operations. So just like refer back to that. I'm not going to repeat myself, but if you're following along until now, so you should know how to perform matrix multiplications by now. Cool. So this was for net inputs. And then we have the activations. So if you remember, when we studied the artificial neuron as an individual computational unit, we said that the artificial neuron does two things. The first part is performing the net input, the weighted sum, as we saw it. And then the second part is the activation itself, which is basically modulating the net input using a function. And we can easily rewrite the activation for all of the neurons in a layer by using like this simple formula here. So the activation of the second layer here, which is a vector, because it is a vector with like 3 values. So there's one activation for S1, one for S2, and one for S3, is given by the activation function f, which in this case is quite abstract, but we'll see later on an example where we have an actual activation function, which is the sigmoid function. And we want to pass H2, so the net input vector for the second layer down here, we want to pass it to the activation function. So right, so let's just recap. So we have the basic elements of a neural network for like its computations are the weights, the net inputs, and the activations. So now let's take a look at the computation in a multi-layer perceptron step by step using some kind of like abstract notation first, and then we'll move on and see an example just like to clarify everything. So as we said, the information travels from left to right. So we start with x, which is the input vector. So it's like these two values here, x1, x2. And then the information, the signal moves to the second layer, and the second layer performs two things. As we saw, we have the net input first and then the activation. So the net input is given by the matrix multiplication between the vector input x and W1, which is the weight matrix for the connections between layer 1 and layer 2. Then when we have H2, we can plug it into the activation function f, and we get the activations vector for the second layer, which is basically the output of the second layer. Now we want to pass this information to the third layer, which in our case is the output layer. So H3 is again the net input, but this time for the third layer, and we can calculate that multiplying the activation vector for the second layer with W2, which is the weight matrix for the connections between the second layer and the output layer. Now that we have H3, we can plug H3 into the activation function f, and what we get is y, which is the output. Now, I know that this was like very abstract, but I wanted to give you an idea of like the notation that we use to understanding, to just like explain how the computation works in a multi-layer perceptron. But now we'll look at an example so that we'll clarify out like all the thing that we've studied so far. So here we have the very same network, but now we have a bunch of parameters in. So 0.8 here and 1 are the two inputs, and then we have all of these weights, so like 1.2, 0.7, 1, and so on for the weights here, the W1 matrix, and here we have these weights for W2, so the weights relative to the connections between the second layer and the output layer. Now, as you can see here, once again, I want to say that this is a fully connected matrix, fully connected neural network, or multi-layer perceptron in this case, because we have that all neurons are connected from a layer connected with all the other neurons in the subsequent layer. Right, so let's get started. So the input vector is just a row vector, and in this case its values are 0.8 and 1. It's these two guys here, which we can call x1 and x2. Right, so now what do we want to do? We want to calculate the computation here in the second layer, and let's just like reiterate that. And the computation does two things there. So the first part is calculating the net input, and the second part is the activation, which again is the output to the subsequent layer. And so in this case, H2 is calculated through a matrix multiplication between the inputs and the weight matrix 1. Right, so now let's plug in the numbers. And so here we have the row vector, which is the input vector here, so 0.8 and 1. And here we have the weight matrix, so this guy here. So all of these weights organized in a weight matrix. And now we can perform a matrix multiplication. So just like very briefly, what we are basically doing here is we're calculating the dot product between this row vector here and this column vector here. And here we have the results for like the first neuron here. And then we shift and we have the result for the second neuron and the result for the third neuron. Now, if we run all of the math there, we come up with these results. And as you can see here, I've just like filled it into the graph, the diagram here. And so 2.96 is the net input for the first neuron of the second layer. 1.56 is the net input for the second neuron in the second layer, and 1.8 is the net input for the third neuron in the second layer. Right, so we've done the net inputs. Now, what should we do? You know it by now. It's the activations. Right, so how do we calculate the activations? It's very, very simple. In this case, we're going to use the sigmoid function. So the sigmoid function, we've already seen it in a previous video on artificial neurons, but it's quite simple. It's a function that it's basically 1 over 1 plus the exponential to the minus x. And instead of x here, we pass in H2. So we pass in all the net inputs. And if we run the math here, we get these results. So we are basically passing the net inputs through the sigmoid function, which is our activation function of choice, and we get back an activation vector where each of these items in the vector corresponds to the activations of the neurons here in the second layer. So we have 0.95, 0.83, 0.86. Okay, great. So we now have the output of the second layer, and we're ready to process the third layer. To get the net input for the third layer, we do a matrix multiplication between the activations from the second layer and the weight matrix for the connections between the second and the third layer. So let's plug in the numbers, and as you can see here, there's an interesting thing, which is that the W2 matrix is actually a column vector. So it's a 3x1 matrix, and that's because we only have one output neuron, and so basically we only have one incoming a connection for each of the neurons in the second layer. So if we perform a dot product here, we end up with 2.99, which is the net input. And now if we want to get to the output of all of this computation, we need to plug that number into the activation function, which in our case is the sigmoid function. So if we do that, basically we end up with 0.95. And so this is the result of the computation of this neural network given all of these parameters. So right, 0.95. It's been like a quite long process, but at the same time, I think like it was quite instructive because you really wanted to understand how a neural network like processes the information on a very detailed level. So before finishing off this video, I want to leave you with a few takeaway points. So we saw first of all that we want to use artificial neural networks when we are dealing with complex problems or problems that have nonlinear solutions, because the way artificial neural networks are arranged with all of these connections and all of this distributed structure with many neurons connected together is very good for reproducing highly nonlinear functions. And as we saw throughout the video, the computation that happens in a neural network and in a multilayer perceptron in this case are distributed. So we have single neurons that do individual computations, and then all of this information is passed on to like other neurons. So another important thing that we saw here is that in a feed-forward network, like a multilayer perceptron, the signal moves from left to right. And finally, I want just like to reiterate the fact that the important elements of a computation in a neural network are the weights, which are represented with matrices, the net inputs, which are represented as row vectors, and activations, which again are represented as row vectors and are the outputs of a layer onto the next layer. Cool. So this was it for this video. And you may be wondering, so what's up next? Well, we've done the theory behind multilayer perceptions and neural networks. So now we're going to have the fun part, which is coding a multilayer perceptron from scratch, only using Python. Cool. So I hope you've enjoyed the video. If that's the case, just leave a like. You can subscribe. And if you have any questions, please feel free to leave a comment in the comment sections below. And that's it for now. And I hope I'll see you next time. Cheers.